everyone. Myself Priyanka Sharma, Assistant Professor, Department of Computer Science and Engineering, USTM. So here today we are going to discuss the basic concept of theory of computations, and the contents of today's lecture basically includes basic concept of automata theory, terminologies used in automata theory, concept of clean star and clean closure, definition of finite automata, types of finite automata, and the summary of the contents. So, the basic aim of the theory of computation course is basically to provide students with a comprehensive understanding of fundamental concept and principle related to computation and its theoretical foundations. So the basic objective of this course is to introduce foundational basically concept of automata theory and develop problem solving skills, explore computational model, and study computability and complexity of a particular problem. So these are the objective of the course. Now, what is automata theory? So, automata theory is basically it is a theoretical concept or theoretical branch of computer science and mathematics, and it is a study of the abstract machines and the computation problem that can be solved using the kind of machines. And the abstract machine is called the automata. Automata means the automatic machines. And the main motivation behind developing the automata theory was to develop methods to describe and analyze the dynamic behavior of a discrete systems. So this automata consists of states and transition. Automata means machines. Automata or machines consist of states. States means uh, a machine can move from one state to another state. That means number of transition required to move forward or backward for machines. So these stages basically known as the states, and the transition from one stage or one state to another state is known as the transitions, and it is denoted by a arrow. So basically it is a theoretical concept, and the state here, the state is represented by the circles and transitions is represented by arrows. Automata, that means machine, is a kind of machines, is a powerful machines which take some strings as input. Now string is what? String is a collection of input input characters. It may be numbers, uh, it may be special characters also. So which takes string as an input, and this input goes through a finite number of states, that means finite number of stages, and may enter the final state. That means we can say that the states of a machine or automata can be divided into two types. One is the initial state and another one is the final state. So now the basic terminology used in case of automata, basically the symbols. So symbols is what? Symbols are the entity or individual objects which can be any letters, alphabet, or any pictures. So symbols, the collection of symbols, we can say that the strings. So it may be a collection of characters, it may be a collection of letters, alphabets, or special pictures. Now what is alphabet? Alphabets are the finite set of symbols, and it is denoted by the sigma. Sigma, basically the symbol sigma denotes the alphabet here. So now for example, sigma equal to a comma b, here This mathematical term we can call it is a collection of input string which consists of symbols a comma b. Similarly, sigma equal to capital A comma capital B comma capital C comma capital D means it is a collection of strings or collection of alphabet which contain symbols capital A, B and C and D. Similarly, sigma equal to 0, 1, 2, that means it is a collection of alphabets or collection of symbols which is known as alphabet, and these symbols includes 0, 1, 2. Similarly, sigma equal to 0, 1 up to 5, it is also a collection of alphabet or symbols which consist of number from 0 to 5. So this is how we can represent a alphabet by using a special symbol which is known as the sigma symbol. So next terminology is known as string. String is what? It is a finite collection of symbols from the alphabet, and the string is basically denoted by W, or sometimes it is denoted by small s also. So here I'm giving few example. So example 1, if sigma equal to a comma b, that means it is a various string that can be generated from sigma are AB, AA, AAA, BB, triple B, BA, ABA. That means we can say that sigma A comma B, that means these alphabets can generate numbers of, that means various strings which consist of AB or double A, triple B, double B, like that. And a string with zero occurrences of symbol is known as basically a empty string. That means empty string is what? If if a string which doesn't contain any symbol, that means the string is known as the empty string and it is denoted by epsilon. And the number of symbols in a string W is called the length of a string, and length can be calculated by using modular symbol. So that means what? If W equal to 0, 1, 0, that means length of W is equal to 3, mod of W equal to 3. If W equal to 0, 1, then that means the length of W should be 2. Next terminology is languages. A language is a collection of appropriate string, and a language which is formed over alphabet can be finite or infinite. So for example, L1, suppose L1 is a language, it is a set of string of length 2, that means it contains string a, B, 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 A, and B, B over input alphabet A, B. And this language is basically a finite language because here the length is given, length is constant. That means the string of length 2. That means this A, B, B. These are the collection of symbols, and this string symbols basically having length equal to 2. Therefore, it is basically considered as the finite languages. Similarly, for example number 2, L2, suppose L2 is a set of all strings start with A. That means it contains string A, double A, triple A, 4A, 5A, like that, or ABB, ABBB, or ABABB. That means it is an infinite language. Here the range is not given, the length of the string is not given. That's why it can generate a string having A at the starting position, and it can generate infinite number of languages. That means infinite string, infinite length of string. So these two are the language. One is finite language, one is infinite language. Now next, move to the next point. The next point is the Power of an alphabet. So alphabet already we have discussed. Alphabet is a collection of string. Now what is power of an alphabet? So here the clean star or clean closer concept arises. Now what is clean star? So definition of clean star is basically it is a unary operator on a set of symbols or string alphabet that gives the infinite set of all possible string of all possible length over a input alphabet sigma including the empty string. So the definition of clean star is basically length of it is a collection of all string over a input alphabet sigma but including the empty string also. And the representation of clean star is basically sigma to the power star. So it is a collection of sigma 0 union sigma 1 union sigma 2 union sigma n. That means sigma 0 here indicates strings having no symbols. That means the empty string. Sigma 1 means string having only one symbol. Sigma 2 means string having only two symbols like that. So it is a collection of all string having all possible length including the empty string. This is the definition of clean star. Now what is clean closure or it is also known as clean plus. So definition of clean closure is the infinite set of all possible string of all possible length over input alphabet sigma but excluding empty string. So this is the difference between clean closure and clean star. So clean star means it is a collection of all string with all possible length including empty string, but clean closure on clean plus means it is a collection of all possible string with all possible length but excluding the empty string. Now here is a representation of clean closure. That means sigma to the power plus is the representation of clean closure which is equal to sigma 1. That means alphabet having one symbol union alphabet having two symbols union alphabet having three symbols union alphabet having n number of symbols. Now sigma plus that means sigma to the power plus clean closure is equal to clean plus that means sigma star minus the empty string. So this is a mathematical formula of clean closure or it is a relationship between the clean closure and sigma star. Now if the sigma is an alphabet then we can express the set of all string of a certain length from that alphabet by using exponential notation that means sigma to the power k. The set of string of length k each of whose is in sigma. Sigma means it is a collection of string or we can say that alphabet. For example, sigma to the power 0 equal to it is a collection of states regardless of what alphabet sigma is. That is q is the only string of length 0. That means we can say that in a simple word sigma to the power 0 means the collection of string having length 0. That means it is a string, it contains string having length 0. If sigma equal to 0, comma 1, then sigma 1 means it is a collection of string having length 1. Similarly, sigma 2 means collection of string having length 2. For example, sigma equal to 0, comma 1, that means we can find out sigma to the power 1. That means we have to add only the string having length 1. That means 0, comma 1. Similarly, sigma to the power 2, that means we can add only the string having length 2. That means from 0, comma 1 alphabet, we can generate string 0, 0, 0, 1, 1, 0, 1, 1. That means all string having length is 2. Similarly, sigma to the power 3 means all string. We can include all string having length 3 over input alphabet sigma 0, comma 1. So we can generate 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1 string. Now the confusion between sigma and sigma 1. So sigma is an alphabet and its member 0 and 1 are the symbols, and sigma 1 is a set of strings. Its members are string, each one of the length 1. Now clean star. Clean star means what? Already we have discussed that the clean star is a set of all string over input alphabet sigma, but including the empty string. So here the 0, comma 1 whole star means we can generate all string having all possible length including the empty string. So here the small q, it denotes basically the empty string. We can define empty string as epsilon also. Epsilon symbol we can use also to define an empty string. But here I am using small q. So small q, comma 0, comma 1, comma 0001, like that we can generate number of strings having different number of different length of string including the empty string. The symbol star is called basically the clean star and is named after the mathematician and logician Stephen Cole Klein. Now the clean plus equal to sigma 1 union sigma 2 union up to sigma n. Thus, we can represent clean star equal to sigma plus union the sigma to the power 0. That means including, that means sigma plus means all string having all possible length, union the sigma to the power 0 means string having only length, string having alphabet having string which length only 0, that means the empty string. Now move to the concept of automata. Now what is the finite automata? Because already we have discussed that automata is basically a machine which consists of states and transition. Now what is finite automata? So finite automata basically are used to recognize basically patterns, and it takes the strings of symbol as input and changes its states accordingly. When the desired symbol is found, then the transition occurs. So at the time of the transition, the automata can either move forward, or we can say that it can move to the next state or stay in the same state. The finite automata have two states. One is accept state, or we can say that the final state, and another one is the rejected state. When the input string is processed successfully and the automata reaches its final state, then it will accept. Now, see the formal definition of finite automata. So, the finite automata basically is a collection of five tuple. Five tuple basically includes capital Q. Capital Q is basically defined as a finite set of states. Then next one is sigma. Sigma is defined as a finite state of input symbol. Next one is delta. Delta is defined as a transition function. Then next one is Q naught. Q naught is the initial state. And last one is capital F. Capital F is basically denoted as the final state. So final automata, the formal definition of final automata is basically is a collection of five tuple which includes capital Q, sigma, delta, Q naught, and F. Now type of automata is basically divided into two types. One is deterministic finite automata and another one is non-deterministic finite automata. Now deterministic finite automata, in short we can say it as a DFA, and non-deterministic finite automata, in short we can say it as NFA. So now what is DFA? DFA refers to the deterministic finite automata. Deterministic means to the uniqueness of the computation. In the DFA, the machine goes to one state only for a particular input character, and DFA doesn't accept the null move, whereas NFA stands for non-deterministic finite automata, and it is used to transmit any number of states for a particular input. That means for a particular input, NFA can move uh, different, that means more than two states, and each can accept the null move also. So this is the difference between DFA and NFA. DFA cannot accept null move, but NFA can accept null move. So some important point about DFA and NFA. So first point is DFA is NFA. That means DFA we can consider as NFA, but NFA we cannot consider as DFA. Then second point is there can be multiple final state in both NFA and DFA, and DFA is basically used in lexical analysis in compiler design, whereas NFA is more of a theoretical concept. So practically basically DFA is more suitable than NFA. Now, what is transition diagram? So, transition diagram or state diagram is a directed graph which can be constructed as follows. So, there is a node for which state in Q, capital Q, basically denoted as a state, and which is represented by a circle, and there is a directed edge from node Q to node P, label A, if transition, that means delta q comma a equal to p. That means if after accepting input alphabet a, q state can move to its p state, and which can be represented by a transition function delta. In the start state, there is an arrow with no source. That means we can identify a starting state with an incoming arrow without any string. Then that state basically represented as the starting state. Then accepting states or the final states are indicating by a double circle. So some notation basically used in case of transition diagram is here the Q1, the circle represents the states, arrow represents the transition from one state to another state, and the circle with incoming arrow without any input string is basically represented as the initial or starting state, and the double circle, that means Qn, basically represented as the final state. So these are the basic notation or mainly most most importantly used notation in case of transition diagram. Now move to the formal definition of DFA. So basically DFA can be represented by a 5 tuple capital Q, sigma, delta, Q and F, where capital Q is a final state of states, sigma is the final state of input symbol which is also known as alphabet, and delta is a transition function, and here transition function maps Q into sigma tends to capital Q, and small q is denoted as the initial state from where any input is proceed, and capital F is a state of final state. That means we can say that capital F is a subset of capital Q. So this is the formal definition of DFA. Now graphical representation of DFA is basically DFA represented by a graph called the state diagram, and the vertices represented the states, and the arrows between two vertices basically represent a transition from one state to another state with an incoming symbol, and the initial state is denoted by a empty single incoming arc, and the final state is indicated by double circle. So this is a graphical representation of DFA. So here is the example of DFA. So let a deterministic finite automata be capital Q equal to ABC. That means this machine or DFA having basically three states, different states A, comma B, comma C. and sigma equal to 0 comma 1, that means it indicates the DFA contain input symbol 0 comma 1. Small q is equal to a, that means here the a state, basically we can consider a as the initial state, and capital F equal to c, that means here c state we can consider as the final state. So here this one is a transition diagram of the given example. So here it is very clearly noticeable that the state A is the initial state. So after accepting input alphabet 0, state A can remain in its own state, but after accepting input alphabet 1, state A can move to its next state, that means state B. Similarly, here in case of B, after accepting input alphabet 0, B can move to its next state C, but after accepting input alphabet 1, B can transit from B to A. Similarly, for C also, after accepting input alphabet 0, C can move back to B, but after accepting 1, C can remain in its own state, and here C represent the final or acceptance state. So this is the graphical representation of the given example, and this is the transition table. Here all the transition or present states are given and input symbols are given, and after accepting the particular input symbol, the present state can move to its next state, that is basically shown here in this transition table. So this is basically the diagrammatical representation of DFA. Thank you so much. So next class we will continue the construction part of DFA.